Okay, let's start today's lecture. Today we're going to continue our discussions about the rules of probability. In particular, we're going to talk about the Bayes theorem. So do you remember in our previous lectures, we talked about the additional rule and the multiplication rule? And what does it mean, the additional rule? When we validate the additional rule? Or, right? So it is like a probability of the A or B, right? It is when we are going to validate the sum of these two probabilities. But we need to be careful because depending on the two events are mutually exclusive or not, the formula is going to be slightly different, right? So what does it mean that two events are mutually exclusive? Two events are mutually exclusive. No. Mutually exclusive. If the two events don't have the intersection, right? For example, well, so let's say one event is going to be rolling a die and getting 5, and the second event is rolling a die and getting 3. So they don't have the intersection. So they're going to be called as a mutually exclusive. So in this case, if you would like to validate the probability of the A or B, you just simply sum. Otherwise, you need to subtract the probability of the intersection, right? Okay, so there is another rule which is called the multiplication rule, but there are two versions of the multiplication rule. One is when you're going to validate the probability of the intersection of these two events, or when you're going to validate the probability of the two events happening in a sequence. So when you are going to validate the probability of the two events happening in a sequence, exactly like the first event happens, then second event happens, we need so-called conditional probability. So the conditional probability of the P of A given A, P of B given A means that you're evaluating the probability of the B when A has already happened. Okay, so when you are going to write down this expression mathematically, like probability of the B, P of B. Okay, so if you would like to write this down in terms of the words, it is going to be probability of B. So at the same time, if I write PBA, well, what is the meaning of the PB of A? So it is still you're evaluating the probability of A, B, okay? So you're still evaluating the probability of the B. So it is going to be the probability of B, but with an additional information that A has already happened. Okay, so this is some notation which you need to know, like a P of B. So every time you're evaluating the probability of this first letter, okay, just after the P. So sometimes you might be given some additional information, sometimes not. Depending on whether this is given, we are going to validate the probability differently. So now, if you would like to know what is the probability that A happened in the first trial, then B happened in the second trial, the most logical way would be to validate this using this way. Okay, so if I say what is the probability that you choose, for example, a jack from the standard deck of cards, then you choose the queen. Okay, so in this case, you're going to validate the probability of choosing a jack in the first trial, okay, times the probability of choosing a queen when you know that the first one is jack, because you want these events happen exactly in the sequence, okay? So the first one should be jack, second one should be queen, okay? So let's do this together. So what is the probability that if you choose two cards without replacement? So without replacement means that you choose the cards, but you don't never put them back. Okay, so the first card is going to be the jack, and the second card is going to be the queen. So it is going to be the probability that the first one is jack times the probability that the second one is queen when the first one is jack, right? So we know that this makes sense, right? This is super logical that you're going to validate the probabilities in the sequence when you want that all of these events are going to happen exactly as you want, okay? So we can evaluate this quickly. So what is the probability of choosing a jack? 4/50t, because there are 4 jacks, right? And choosing one of them is 4/50t. What is the probability that the second card is going to be the queen if the first one is jack? 4/51, right? You understand what's going on? There are 4 jacks. Yeah, yeah. Yes. There are 4 jacks, 52 cards, okay? Probability of choosing one of them is 4 over 52. So now you know that the first one is jack, right? You know that there are 51 cards there left, and you know that there are 4 queens still there. Probability of choosing one of them is 4 over 51, okay? Cool. So we can evaluate the probabilities like this. So when you have got the set, like the cards, you know that probability of all of the events or all of the cards are equally likely, and we can evaluate the probabilities like this. Okay, but at the same time, so we need to be able to evaluate the probabilities empirically. So depending on some data. Okay, so fortunately for you, usually I'm not late for your group because this is the second lecture. But if you would be at 9, you would know that I'm late every time. Okay, so if you have got some statistics, let's say, oh, so this is the formula which we're going to use. Could you please write this down? So most of the time, we are not interested or we don't want to evaluate the probability of the A and B. Okay, most of the time we would be interested to evaluate the probability of B when A has already happened. Okay, so evaluating this is easier than evaluating this. This is what I want to say. So evaluating probability of the A and B is easier than the probability of the evaluating the B when A has already happened. Okay, so most of the time we would be interested to evaluate this. So that is why we need this formula. So this is a simplified version of so-called Bayes theorem. So this is what we're going to discuss today, and we're going to discuss how to use this Bayes theorem. So it is always confusing to memorize this formula. So I would like to give you some hints how you can memorize this formula. So if you're evaluating the probability of the B when A has already happened, so you need to write this down as the ratio of the 2 probabilities, okay? So on the denominator, it should be always the second letter should go. So the second letter should always go to the denominator. On the numerator, you need to write down the A and B. Okay, so this is one of the ways how you can memorize this formula. So today, I would like to start today's lecture with doing some exercises on empirical statistics, okay? So let's assume that you've got some statistics of the number of the time when I'm late to the lectures, okay? So you made a record. So I know that during one of the semesters, some students made the record of me being late to the lectures. And he made the full statistics, like how many times I was late, how many times, and how much I was late. Okay, and at the end of the semester, he wrote down this survey review, like a survey review in the INS, and he wrote down the statistics and he made the analysis. So he wrote down the distribution and so on. So it was kind of cool. So let's assume that I was late. So after 10 lectures, you've got a small statistic. Like I was late for 7 lectures and not late for the 3 lectures. Okay, do you understand this? 7 lectures I was late, 3 lectures I was not late. So what is the probability that I'm going to be late on the 11th lecture? You've got a statistics for the 10 lectures, okay? I was late for 7 of them and was not late for 3 of them. So before the 11th lecture, you're discussing with your friends and you would like to evaluate the probability that your professor is going to be late again. 7 over 10. Okay, so this is a way how we are going to evaluate the probability when we've got some data. Okay, so when we are going to obtain some statistical data, we can evaluate the probabilities of some event by just dividing the frequency of that event to the total number of the frequencies. Okay, so the probability that I'm going to be late, the frequencies is 7, right? So I was late 7 times, and the total frequencies is 10. So that is why I'm still dividing this to the 7 over 10. Okay. So now we're going to evaluate the probabilities in the same way for this problem, okay? So what we did is we collected the result of the 98 subjects, 98 persons who went through the polygraph test. So the polygraph is an instrument which allows you to identify whether a person is lying to us a particular question or not, okay? So you know how it works, right? So you plug in lots of lots of instruments to you, and someone is going to ask you a question. And if you lie, the instrument is going to tell you that the subject is lying. Okay? But obviously, this polygraph instrument doesn't work perfectly, and it has some error. Okay? So when the polygraph test is positive, we call this positive. It means that the polygraph is claiming that the person is lied. Okay? So what's your name? Alisher, for example, has lied, and the polygraph test gives me the positive result. Okay? If he doesn't lie, the polygraph test tells me the negative result. Okay? So the positive means polygraph indicates that the person is lying. Okay? Negative means polygraph test indicates that the subject did not lie. Okay? But it is possible that, for example, Alisher has lied. Okay? But the polygraph resulted negatively. Right? Do you understand this? So Alisher did not lie, okay? Did not lie, but the polygraph result negatively. Negatively means, oh, he lied, sorry. I'm sorry. So Alisher lied, okay? He actually lied, but the instrument tells me that he didn't lie, okay? So negative means instrument tells that he didn't lie. Okay, this is an error, right? But there is another type of the error. So this happens when Alisher, for example, indeed didn't lie. Okay, he told the truth here, right? But the instrument tests positively. It means that instrument claims that he's lying. Okay, do you understand this? So what we want, of course, we want this kind of errors are going to be very small for our instrumentations. So in order to do this, we're going to evaluate some probabilities, okay? So let's evaluate the probability. So this is a very cool table where we are going to evaluate the probabilities and conditional probabilities very easily. So let's assume that there are 98. Did you understand the table? What does it mean, all of this table? Right? So if you go to the polygraph test, it is going to give you two answers, either positive, either negative. If it tells positive, means that you lied. Negative means you didn't lie. Okay? But there is also another truth inside you, right? You know that, for example, you lie or you didn't lie. Okay? So you might lie, but the test shows you a negative answer, or vice versa. Okay? All of these results are given here. There are 98 persons who passed through this test. We're going to choose one of them. What is the probability that this person had a positive test result? So how to evaluate this? Do you understand the question? I mean, you can adopt. If it is difficult for you to understand this with the polygraph, you can easily adopt this test with the COVID. Okay, I mean, like a positive test result, negative test result, like a positive when you don't have this virus, or positive when you have this virus, or negative when you have this virus. There are lots of different possibilities, right? There are 4 possibilities. Okay, you choose one person. What is the probability that this person had a positive test result? So what we need to do is, say we are going to use the data, right? Okay. So probability that the test is positive is going to be equal to. So now I need to figure out how many people had a positive test result. How many? 57. Okay. And how many people have been tested by the polygraph? In total, 98. Okay. So it is like this. So there are 98 persons who passed through this polygraph test in total, and 57 of them had this test positively, and the rest 41 of them had this test negatively. Okay, I'm asking you, if you choose one person, what is the probability that he's going to be from this part? Obviously 57 over 98. Okay, do you understand this? Are you writing this down? So let's do this problem a little bit differently. So now you choose this person, one of the persons, okay? What's your name? Huh? Alexander. So I choose Alexander, and I know he lied. Okay, he went through the positive test. I know that he lied. What is the probability that polygraph tested positively for him? I mean, it's super important, right? So I want that if a person lied, the polygraph should test positively for most of the cases, okay? So I would like to know, hey, if he lied, what is the probability that the polygraph showed this positively? Okay, now the sample space is going to be different, right? Because I know that he already lied. So I need to choose only the people who have lied. So how many people who have lied? 51. 51. There are in total 51 subjects who lied, okay? And I know that for 42 of them, the test was positive, and for the 9 of them, the test was negative, okay? And the probability that for Alexander, it is positive if he lied is going to be equal to the 42 over 51, okay? The sample space is going to be different. So this is how it works. Oh, by the way, so let me change this problem a little bit. So what is the probability if a test is positive, what is the probability that he lied? What's your name? Amir. So I know that for Amir, the test was positive. What is the probability that he lied? But I mean, because it doesn't mean that he lied, right? So it is possible that he didn't lie, but the test was positive. What is the probability that he lied if the test was positive? So now again, we are going to create a sample space, right? So in our case, the sample space is going to be all the people who had the positive, right? This is going to be our sample space. And we're going to split this into the 2 parts, okay? People who lied and people who didn't lie, okay? And the probability that Amir didn't lie if his test was positive is going to be equal to, or he lied, sorry, right? It's going to be 42 over 57. Okay, so you see, so most of the time, so like a probability of the A given B and probability of the B given A are different. Okay, so this probability is something different than simply the intersection. Okay, so if I say, by the way, there is a third possible way, right? What is the probability that the person, I will choose the person who had a positive test and he lied? What is the probability of this case? What is the probability that the person has a positive test result and lied? 42 over 98. Okay, this is going to be the intersection. 42, this is the number of the persons, number of the subjects who lied and who had a positive test out of all of the 98. Okay, probability that a person who had a positive test and lied is going to be equal to the 42 over 98. Okay, so I hope that you feel the differences in all of these cases. Okay, so here when this after the slash you're given some event, it means that this has already happened, that you're going to have the new sample space always. Okay, so most of the time in practice we are going to evaluate the probability using the empirical way. So this is called the empirical way. You collect some statistics, and if you would like to evaluate the probability of a certain category, you're going to just divide the frequency of that particular category to the total amount of the frequencies. Okay, so this is how it works. So today we are going to talk about something different. So we're going to talk about the Bayes rule. But before we talk about the Bayes rule, I would like to start with something which is called like a law of total probabilities. So I would like to understand this law of total probabilities from the perspective of the sets. Okay? So let's say I've got the sample space. So do you remember what was the sample space? So the set of all of the outputs of your experiment is the sample space. And what is the event? Is only some part of the sample space. Okay, so let's say I'm going to choose some B. This is going to be some part of the sample space. Could you please tell me what is the B prime? Okay, so everything outside the B. Okay, so if B is everything inside, right, then the B prime is going to be everything outside. Okay, so this is going to be the complement. Okay, so now let's say I've got another event A. Okay, so another event A, and let's say they have the intersection. Could you please tell me, by just looking through this picture and by just understanding what is the B, B prime, and A, what is the intersection of the A and B prime? What is the intersection of the A and B prime? A and B prime. Where it is? This is going to be the intersection. So the B prime is everything outside the B, right? Intersection means like all of the regions together, okay? And so everything outside the B is going to be B prime, okay? And everything inside the A is going to be A. The intersection is going to be everything which is inside the A but outside the B, right? Or it's going to be like this. This region is going to be AB prime, right? I hope that you understand this. So this is going to be the intersection of the A and B prime, right? I'm still outside the B, but inside the A, right? Okay, at the same time, could you please tell me what is the intersection of the A and B? I mean, it's easy, right? So this region is going to be the intersection of the A and B. Okay, so now what I want is I would like to find A as the union of the AB prime and AB. Okay, so the intersection, union of the AB prime and AB is going to give you what? Which set is going to give A? Okay, so you will understand in a moment why we need this, but now you just need to understand what does it mean. Okay, so where it is coming from. So probability of the A, or simply the A, is going to be union of the AB and AB prime. Okay, so that is why probability of the A is going to be the probability of the AB plus the probability of the AB prime. Okay, at the same time, if you remember previously, so this AB means A and B, right? Or AB prime means A and B prime. So I'm just writing this without and, okay? So we know that we can open the brackets using the conditional probability, right? So you can, if you open the brackets as a conditional probability, you're going to get this kind of equation. So essentially this AB can be written as the A given B when B has happened, okay? Plus the probability of the A when the B prime happened times the probability of the B prime, okay? So this law is very important law. It is called like a law of total probabilities, okay? Could you please write this down? We're going to now discuss this together a little bit. The law of total probabilities. So it appears I put one problem here. We are going to come back to this problem in a moment, okay? So let's discuss about the law of total probabilities first of all. So let's say I've got a box. So there are 5 balls inside the box. 3 of them are red and 2 of them are yellow. If I choose one of the balls randomly, Alexander, what is the probability that it is going to be red? 3 over 5, right? And the probability that if I choose a ball randomly, it's going to be yellow is 2 over 5, right? Do you agree? Okay. Now, let's choose 2 balls in a row without replacement, okay? It means I choose one ball, I don't put this bag, then I choose the second ball, okay? What is the probability that the second ball is yellow? Please don't guess. So it's like, I don't need the answer. I need the method how we've got the answer. Okay? So it is super important for us to understand how to get the answer. The answer is itself not so important at this stage. Okay? There are 2 possibilities, 2 scenarios, right? Okay, let's do this together. Do you understand the question? Right? You choose 2 balls in a row. You choose one ball. Don't put this bag. You choose the second ball, right? What is the probability that the second ball is the yellow? Okay. Probability that the second ball is yellow, probability that the second ball is yellow can be happened in the 2 scenarios. So it is either that the probability that the second ball is yellow when the first one is yellow, right? Times the probability of having the first ball is yellow. Or it is possible that the second ball is yellow when the first one is not yellow, right? Times the probability of having the first one not yellow. Okay? So there are two possible scenarios to get the second ball as a yellow. Either the first one is yellow, then the second one is yellow, and this is the probability is going to be like this, right? So this probability, this multiplication of these two numbers, means you're choosing the first ball as a yellow, second ball as a yellow, okay? Or it is possible that it happens when the first ball is not yellow, right? And the second ball is yellow. So this is this probability, okay? So the second ball can be yellow either in this case or in this case, so that is why we're summing these two probabilities. So now if you look to the formula-wise, to this formula and to that formula above, they are the same, okay? So I'm just like denoting the 2y as the A and the B as 1y, okay? They are the same. So this is what does it mean the probability of the law of total probabilities. When you're evaluating the probability of some event, okay, taking into account all of the other scenarios, all of the other events which might affect your event. Okay, so let's evaluate this together. It is important because the next part of the problem depends on the answer of this part. Okay, so let's do this together. What is the probability that the first ball is yellow? 2/5. What is the probability that the second ball is yellow if the first one is yellow? 1/4, right? So I hope that you understand that this is 1/4, right? So it means that you chose one of the yellow balls. There is no yellow anymore, okay? So this is what does it mean? This probability means that you already chose the yellow. There's no yellow here, okay? Then probability of choosing one of them is 1/4 because there are 4 balls left here, okay? Plus, so we need to evaluate the second probability. So here plus, what is the probability of choosing a number without not yellow is 3/5 times the probability of choosing a yellow in the second trial is 2/4, right? So this is going to be equal to the 8/20 or something this, if you sum. Did you get 8/20? Okay, so please memorize this. I think it's going to be 2/5. Okay, so now, if I say you, what's your name? Huh? Danya. What is the probability that the second ball is yellow if the first one is yellow? If the first one is red, sorry. What is the probability that the second ball is yellow if the first one is red? 2/4. Yes? Probability that the second ball is yellow if the first one is red is 2/4. Okay? What if I ask you the question vice versa? What is the probability that the first ball is red if the second one is yellow? Do you understand the question? Okay, so most of the time we need to evaluate such a probabilities. For example, what is the probability that the first ball is red if the second one is yellow? Is already given. Okay, so you choose the two balls, you don't look to the color of the first one. Okay, so you just don't look this, hide this, and then choose the second ball. So you see that the second ball is yellow, and now you would like to go back and you would like to know what is the probability actually the first one is red. Okay, so in order to evaluate this, you see, so when you know the answer, it is a vice versa. When you just swap them, right? You know the answer. But if you just swap them, you don't know the answer. We're going to use so-called Bayes rule. Okay, so when you don't know the answer of the swapped versions, we are going to use the Bayes rule. The formula is going to look like this. Okay, could you please write it down? Probability of the first is red, given the second is yellow, is going to be the ratio of these two probabilities. It is very much similar to the formula which we wrote in the beginning. So if you remember, it was like A and B divided to the probability of the A, right? So I just like open that brackets with the A and B, okay? So one easy way to memorize this formula is always going to be like this. So write down this probability, this conditional probability, as the ratio of the two other probabilities, okay? how to construct these two probabilities. On the numerator, you need to write down again another conditional probability by just swapping these two probabilities with their places. Okay, so this is some method to memorize this formula without understanding this. Okay, so just swap their places and write it down. Okay, then just after the conditional probability, write down the probability of the second event. Okay, so the second just jumps over from the first probability. Okay. Then onto the denominator, what should go is essentially the second probability from here to 2y should go to the denominator. Okay, so this is how I memorize the formula, by the way. Okay, so if I need to validate, so let's do a practice. So what is the probability of d and t? Can you tell me? So is it going to be the probability of t and d, right? I'm just going to swap them. Multiplied to the probability of the d, right? Because the d is jumped over from the formula, divided to the probability of the t. Okay? So this is the easy way how to memorize this formula. Okay? So you just swap them, then the second one jumps over, divided to the probability of the second one comes down. Okay? Now we have to evaluate this probability still. So what is the probability that the first ball is red if the second one is yellow? Let's do this together. So it is going to be equal to this probability. What is the probability that the second ball is yellow if the first one is red? 2 over 4, right? 2 over 4. If the first one is red, probability that the second one is yellow is 2 over 4. Okay? The first one is red means that you're going to just cancel one of the reds. There are 4 balls. You're going to divide the 2 to the 4. So times to the probability that the first ball is red. 3 over 5. Can you check the camera? Is it 30 minutes? Divided to the probability that the second ball is yellow is 2 over 5, right? We just calculated this previously using the law of total probabilities. Okay, so in the Bayes rule, most of the time, this number on the denominator is calculated using the law of total probabilities. 99% of the cases. Okay. So now we're going to just like make the simplifications. It is going to be 3 over 4. Okay, 75%. Okay, before we proceed, so today we're going to discuss 3 more problems on the Bayes rule. Before we do this, let's go back to our problem, because there is a problem, there are a couple of problems, typical problems on this topic from your quiz number 2. Did anyone open the quiz number 2? No, no one. Okay, so there are 3 independent physical experiments are going to be conducted. Okay, so you're going to do the first one, the second one, and the third one. Probability that the first one is successful is 50%. Probability that the second one is going to be successful 60%. And the third one is successful is 70%. If you just do the 3 experiments in the row, the first one, the second one, and the third one, what is the probability that exactly 2 of them are going to be successful? Any 2. But exactly 2. Not at least 2, not at most 2. Exactly 2 of them are going to be successful. In order to evaluate this, you need to consider all of the possible scenarios. Okay? So it is possible that you're going to have 2 experiments successfully if the first one is successful, the second one is successful, and the third one is unsuccessful. Right? So you need to evaluate the probability of the 3 experiments happening exactly in this order, right? So you don't want that the first one may be successful or not, or the second one may be successful or not. You want that the first one have to be successful, second one have to be successful, and the third one have to be unsuccessful, for sure, right? This is one of the scenarios when you might have 2 successful events, successful experiments. Is it the only scenario when you're going to have 2 successful experiments? No, right? There are 2 more, right? So it is possible that it is going to be probability of the 1, 2 prime 3, right? 2 prime means the complement, right? So 3 means experiment is successful. 3 prime means experiment is unsuccessful, okay? Plus the p of 1 prime 2, 3. So since the events are independent, you can write down the probabilities by just like you can write down the 1, 2, 3 prime as just the multiplication of the probabilities. Okay, so they're independent. So the probability of the 1 times the probability of the 2 times the probability of the 3 prime plus the probability of the 1, probability of the 2 prime, probability of the 3 plus the probability of the 1 prime, 2 and 3. So let's evaluate this together. What is the probability of the 1, P of 1? It is given, 0.5. What is the P of 2? 0.6. What is the P of 3 prime? 0.3, right? It is given that the third one is successful, probability that the third one is successful, 0.7. And so that is why the probability that the third one is unsuccessful is going to be 1 minus 0.7, okay? So analogously, we're going to calculate other probabilities. So in this case, it's going to be 0.5 times the 0.4 times the 0.7 plus 0.5 times the 0.6 times the 0.7. Okay? So this is how we are going to use the additional rule and the multiplication rule when we're dealing with the independent events. Okay, so you're basically taking into account all of the possible scenarios and evaluating their probabilities. Okay? Cool. So let's go back to our problem. So this is very much realistic problem. So in an insurance company, people there consider all of the persons, all of the others, in the two categories, like an accident-prone person or not. Accident-prone means this is a person who tends to have an accident. Probability that an accident-prone person is going to have an accident within 1 year is 40%. And the probability that for all the others who are not accident-prone is 20%. Okay? So now, if you assume that 30% of the population is an accident-prone persons, what is the probability that the new policyholder is going to have an accident within 1 year? Okay? So now let's assume that you work at the insurance company. There's a new person came to your office. You would like to evaluate the probability. What is the probability that he is going to have an accident prone? He's going to have an accident within 1 year without knowing whether he's an accident prone or not. Right? Because if we know that he's an accident prone, we know that he's going to have an accident with a probability of 40%, right? So the person came to my office. I would like to know what is the probability that he's going to have an accident within 1 year. Okay, because depending on this probability, I will charge him some money, right? If this probability is high, then I'm going to charge more money. Okay, so let's do this together. So we are going to have this kind of problems a lot of time during this course. So I would like to give you some suggestions. So if you have this kind of problem, so yesterday I spent like a couple of hours to make the structure, how to put the structure of the question so that it is going to be clear to write this down mathematically. Okay, so your first step should be always to write down the text mathematically. Okay, so what does it mean that the probability that the person is going to have an accident if he's an accident prone is 40%? How we can write this down mathematically? How we can write down this mathematically? Probability that an accident-prone person is going to have an accident is 40%. How we can write this down? Okay, so I'm just going to show you the first one, and you're going to have me for the second one. Okay, probability that a person is going to have an accident, if he is an accident-prone, is 0.4. Okay, so can you help me how we can do this for the second one or for the third row? P of A, vertical line, prone, prime, right? Prone, prime. okay? Probability that the person is going to have an accident, if he's not an accident prone, right, is going to be 0.2, okay? So what we need to validate, so what we also know is that the 30% of the population are accident prone. How we can write this down? 30% of the population are accident prone. How we can write this down? P of prone is 30%, right? It means that if I choose any person, right, from the society, probability that he's going to be an accident is 30%, okay? So the P of prone is 0.3, and consequently P of prone prime is 0.7, right? What you need to find is P of A, okay? So I think writing down all of these words in this way mathematically makes your life much more easier. So you can solve this problem much more easier. So what we need to do is we need to write them down together. So what is the probability that the person is going to have an accident? Well, it depends, right? Whether the person is accident prone or not, okay? Probability that the person is going to have an accident if he's an accident prone times the probability that he's an accident prone, or probability that he's going to have an accident if he's not an accident prone times the probability of having a person who's not an accident prone. Okay, so again, so Daniel came to my office. I don't know whether he's an accident prone or not. If I knew, I would definitely tell you whether this is 0.4 or 0.2. Okay, the problem is I don't know this. So that is why I'm taking into account two possible ways. Either he might be an accident prone, either he is not. Okay, so that is why I'm taking the probabilities of these two cases and adding them. Okay, so what is the probability of the first case? What is the probability of P of A prone? 0.4, right? Times the 0.3 plus, so 0.2 times the 0.7. Okay, it's going to be 0.26. Okay, so please remember this number because we need this. Okay, cool. Oh, it is good. Now, so I sold the policy to insurance policy to Dania. Unfortunately, he had an accident. I want to know now, what is the probability that he's actually an accident-prone person? Do you understand the question? So now, within 1 year, the client had an accident. I would like to know what is the probability that the client is actually an accident-prone. Okay, yeah. I mean, first of all, I need to write this down, what I want, right? What I want is, it is the key, actually. So what I want is, I would like to know what is the probability that he is an accident prone if he had an accident, right? This is what I want. So you see, so I know this version of this probability, right? When these two things are swapped, but I don't know this one. So that is why I'm going to use the Bayes rule, right? Can you help me to construct the formula for the Bayes rule? So I need to write this down as the ratio of the two probabilities. What is going to be on the numerator? P A prime times the P of what? Prime, because this prime is going to go out, right? Divided to P of A. Okay, so this is the way how we are going to memorize this formula. So it is going to be equal to, what is the P of A and prone? Or A when it is prone? 0.4 times to the 0.3 divided to the 0.26. It is going to be 12 over 26, or if you divide this to the 2, it's going to be 6 over 13. Okay, cool. So let's do one more example. Yeah, I think this is my favorite one. So let's say, so if you've got a multiple choice question in the midterm on probability and statistics, depending on how well you're prepared, you can get a different scores. Okay, so this is going to be the simulation of your exam, let's say. Okay, So probability that Alexander is not prepared well to the midterm, and probability that he will know the answer is 30%. Okay, if he knows the answer, he's going to correctly answer this for sure. Let's assume that he will be able to do this. Okay, because sometimes even you cannot make this correctly, right? So let's assume that if he knows, he can make this correctly. But the probability that he will get a question he doesn't know is 70%. Okay. So now, if we assume, so there are 4 options for every question, okay? If he doesn't know, he always trying to guess, okay? So probability that he's going to guess correctly one of the answers is going to be 1/4, okay? Do you understand this? So there are 10 questions, let's assume, okay? So probability that if he chooses one of the questions and he knows the answer is 30%. Probability that he doesn't know is 70%. If he doesn't know, he's going to guess. If he guesses, probability that the question is going to be correctly is 25%. Okay? What is the probability that the student knew the answer given that the answer is correct? Okay, so let's assume that after the exam, I'm grading the questions, the answers of Alexander, and the first question is correct. And I'm just curious to know, what is the probability actually he knew the answer? Okay, do you understand the question? Again, so in order to solve this problem, if you don't understand anything, okay, so how to solve this problem, just try to write down everything mathematically, okay, and just put everything down into the formulas. So what does it mean that the probability that he will know the answer is 30%? So I'm just going to put this like a letters. The probability of the k is 0.3, k prime is 0.7. Okay, I hope that you understand this, right? Okay, so what is the probability that he is going to answer correctly, right? If he guesses, how to write this down mathematically? The answer is going to be correctly if he guesses is 0.25. How to write this down? PCKG. So probability that the answer is correct if he doesn't know the answer, if he guesses, right? So now it is fixed that he guesses the answer, and the probability that he's going to answer correctly is going to be 1/4, right? At the same time, by the way, what is going to be the probability of C if he knows? 1, right? I mean, if he knows the answer, he's going to answer correctly for sure, right? We already fixed this, okay? So now, what we need to find is probability of the KC, so the vice versa, right? So what is the probability that he knew the answer if the answer is correct, okay? So this is what we would like to evaluate. And again, we are going to, so we know what is the vice versa, which is like the other version of this. In order to evaluate this one, we need to use, again, the Bayes rule, okay? So can you help me with the Bayes rule one more time? So what is the probability of the K and C? On the numerator, what I have to write? So the P of C given K times the P of K, okay, divided to the P of C. Okay? So what is the probability that he's going to answer the question correctly? No. Here, not this one. This one. So if he chooses one of the questions, okay, randomly, what is the probability that he's going to answer correctly? Well, it depends, right? It depends whether he will know this answer, he will be familiar with this question or not, right? If he is familiar with this question, then probability that he's going to answer correctly is 1, right? But I have to multiply this to the probability that he's going to choose this question, which he knows, right? Or it is also possible that he might answer correctly if he doesn't know the question, times the probability of the choosing the question which he doesn't know. Okay, there are 2 possible scenarios, right? So he can answer question correctly in the 2 possible ways. Either he knows this, either he doesn't know. Okay, but we need to scale these 2 scenarios. Okay, so these 2 numbers are just the scaling parameters of these two scenarios. So let's evaluate this. So it is going to be equal to the 0.3, right? So this is 1, this is 0.3, this is 0.25, and this is 0.7. Can you help me with evaluating this if you have a calculator, please? Okay, so I'm just going to put this together here. So the probability of he is going to answer correctly if he knows is 1 times the probability of he is going to choose a question which he knows is 0.3 divided to the 0.475. It is going to be 3 divided to the 4.75 or something like this. Okay, if all of the calculations are correct, then the answer is going to be like this. I mean, when I mean the calculations with the calculator. Okay, I mean formula-wise, it's correct. Oh, cool. So let's do one more. So let's assume that we're going to use our students to make the analysis of the bank accounts of our employees. So the two students make the data analysis in the bank. Student A makes the analysis of the 60% of the accounts, and student B makes the analysis of the rest. So student A makes the mistake in 1% of the cases. Okay, so he makes the analysis. Making the analysis, maybe let's say just copying or testing them or something. Okay, so the student A makes some mistakes in 1% of the cases. If he makes the analysis of the 100 cases, then one of them is going to be incorrect. Okay, so student B makes the mistake in 2% of the cases. Okay, so now the question is, so now you choose one of the, so as a manager, so manager goes to all of the data sets, just chooses one of the data sets randomly. Unfortunately, there is a mistake. What is the probability that this account was analyzed by the student A? Okay, do you understand the question? Again, we are going to write down everything in terms of the formulas, okay? Could you please help me with writing down the notation? What is going to be the notation for the first row? P of A should be 0.6 and P of B 0.4, right? Yes, because if you choose one of the accounts randomly, probability that this account has been analyzed by the student A is 60%, and probability that this account has been analyzed by the student B is 40%. Okay, so what I can write down in the second row? Probability of the mistake if this account has been analyzed by the student A is equal to the 0.01, right? Do you understand this? So probability that there is a mistake if the account has been analyzed by the student A is 0.01. Okay, so this is how we are going to write it down mathematically, first of all. So what I can do for the third row, P of M slash B, right? The probability that there is a mistake if this is analyzed by the student B is 0.02. And what I can write down for the last one, what I have to write. So could you please tell me what I should find? P of what? A given M, right? So if there is a mistake, what is the probability that this account has been analyzed by the student A? Okay. So again, I'm going to just put this together, and I'm going to use again the same formula as we did before in order to evaluate the probability. So what is the probability of the A given M? So again, you're going to write this down in terms of the two probabilities. On the numerator, you're going to write this down, the P of M given A times the P of A, and all of this divided to the P of M. Okay? And in order to evaluate the probability of a mistake is going to be, okay, so now, if I choose one of the accounts randomly, probability that there is a mistake in this account, right, might happen in two different scenarios, okay, depending on whether this account has been analyzed by the student A or B, okay? So using the law of total probabilities, we're going to evaluate this. Probability that there is a mistake if this was analyzed by the student A times the probability of the A. plus the probability that there is a mistake if this account has been analyzed by the student B times the P of B. Okay? And then we're going to just put all of the numbers together. It is going to be 0.01 times the 0.6 plus 0.02 times the 0.4. Can you help me with the calculations? 0.014. Okay, cool. So I'm just going to put this to here. It's going to be 0.01 times the 0.6 divided to the 0.014. It is going to be 6 over 14. Okay, so if I choose an account and if there is a mistake, probability that this mistake was done by the student A is equal to the 6 over 14. Okay, so you see, so the Bayes rule is super useful when we are evaluating the conditional probability. So evaluating the and is not a big deal most of the time, but evaluating the conditional probability is a problem. I mean, which we need to deal with. And the Bayes rule is always helpful for us to do this. And also, we need to know about this very powerful law of total probabilities. Okay, so I hope that you understand all of these topics. Okay, thank you very much for your attention. See you.